Welcome. Today's lecture covers software development lifecycle models, commonly abbreviated as SDLC, along with agile methods. This is one of the most practically important topics you will encounter as a computer science student here at Lusaka Goldsmiths University. The way software is planned, built, and delivered has evolved dramatically over the decades. By the end of this lecture, you will understand the major approaches, their strengths, their weaknesses, and how to think critically about which one to apply. Let us begin with a question. How did software development lifecycle models come about in the first place? The answer lies in an analogy with civil engineering. When you build a bridge or a building, the process is straightforward. You design first, then you construct. The design phase produces blueprints. The construction phase follows those blueprints. Early software engineers tried to apply this same thinking to software. Design first, then build. But here is the fundamental problem. In civil engineering, construction is a distinct physical process. You are pouring concrete, you are welding steel. That is genuinely different from drafting the blueprints. In software, there is no equivalent of construction. Writing code is design. All of it is design. There is no physical assembly step. This distinction was not well understood in the early days of the field. Software used to simply be called coding, and the assumption was that if you designed carefully enough up front, writing the code would be straightforward. That assumption led to a lot of troubled projects. The rest of this lecture is largely about what went wrong and what people tried to do about it. This slide shows a diagram illustrating the software development lifecycle at a high level. Think of it as a map of all the activities involved in taking a software product from an initial idea to a working deployed system. Typically, such a diagram shows stages like requirements, gathering, design, implementation, testing, deployment, and maintenance arranged in some kind of sequence or cycle. The key insight the diagram is trying to convey is that software development is not a single act. It is a structured journey through multiple phases, each of which feeds into the next. Different SDLC models make different choices about how these phases are ordered, how much overlap is allowed between them, and whether they repeat. Before we dive into specific models, let us ask two foundational questions. First, what is a software development process? A software development process is the structured set of activities, roles, tools, and decisions that a team uses to go from an idea to a working product. Second, what is the lifecycle of a software project? The lifecycle is the full span of time and activity from the first conversation about what the software should do, all the way through to when it is retired and replaced. Now, you will hear the word agile used a lot. We will get to agile, but first, we need to understand the traditional approach that agile was reacting against. You will hear that traditional approach described by many names: disciplined, planned, structured, sturdy. None of these names have quite stuck. What has stuck is the contrast with agile. Keep that contrast in mind as we go through the models. We are building up to understanding why the software industry felt it needed something different. The software industry tends to discuss development processes in terms of a dichotomy: agile versus everything else. You will often hear it framed as agile versus planned or agile versus traditional. There is also a common misconception worth addressing directly. Some people assume the deployment model tells you what development process was used. For example, if software is delivered as a web service, it must have been built with agile methods. If it is installed software, it must have been built traditionally. This is incorrect. The development process and the deployment model are independent choices. A team can use agile methods to build installed desktop software. A team can use a traditional waterfall approach to build a web service. The better way to think about it is this: apply the process at the level of individual features or at the level of an entire release. The unit of analysis matters. Continuous delivery of features is an agile concept, but it can coexist with careful planning at the release level. This slide shows a diagram of an example feature workflow. Let me explain what this represents. A feature workflow is the sequence of steps that a single feature goes through from the moment someone decides it needs to exist to the moment it is live in production. A typical feature workflow might look like this. First, a feature is requested or identified. Someone writes a description of what it should do. Then it enters a planning queue where the team decides when to work on it. Then a developer picks it up, writes the code, and writes tests. Then it goes through code review. Then it is integrated into the main code base. Then it is tested at a higher level. Then it is deployed. The diagram is making the point that even a single feature is not a simple task. It has its own mini life story. Understanding this helps you see why process matters. Without a defined workflow, features get dropped, duplicated, or shipped untested. The workflow is the skeleton that keeps the work organized. So, what are we actually trying to achieve with an SDLC? What does success look like? There are 4 dimensions of quality to consider. The first is external quality. Does the software pass all its tests? Does it do what users expect? This is the most visible form of quality. Users experience it directly. The second is internal quality. Is the design good? Is the architecture clean? Internal quality is invisible to end users but critical for maintainability. Good internal quality means future changes are cheaper and safer. The third is quality in use. Does the software provide a good user experience? A system can pass all its tests and still be frustrating to use. Quality in use asks, does this actually serve the people who use it? The fourth is process quality. Can the process itself help ensure product quality? A good process catches defects early, reduces rework, and keeps the team aligned. A good SDLC is one that helps teams achieve all 4 of these qualities consistently across projects of different sizes and complexities. The first major SDLC model is the waterfall model. It is the model that many others were designed to improve upon or replace. The waterfall model organizes development into a sequence of phases: requirements, design, construction, integration, debugging, installation, and maintenance. The defining rule of waterfall is strict. You move from one phase to the next only when the preceding phase is completely finished and formally accepted. Now, here is something important about the history of this model. It was first described by Winston Royce in 1970, but Royce described it as an example of a flawed, non-working model. He was warning against it, yet the industry adopted it anyway. The United States Department of Defense actually mandated a version of waterfall for their contractors through a military standard called DoD-2167. Contractors had to produce the specified deliverables for each phase and have them formally accepted before proceeding. The problem with that mandate is that the problems with waterfall run deep. Let us go through them. First, it takes a static view of requirements. Requirements are treated as a fixed document that is agreed upon once and then frozen. But requirements are not static. Users change their minds. The business environment changes. The technology changes. Treating requirements as immutable ignores this fundamental reality. Second, there is almost no user involvement after the requirement specification is written. The user participates at the beginning to describe what they want, then disappears for months or years while the team builds it. When the software is delivered, it often does not match what the user actually needed because needs evolved. Third, the separation between specification and design is unrealistic. In practice, you cannot fully specify a system without making design decisions, and you cannot fully design without discovering gaps in the specification. The problems with waterfall continue. Waterfall projects were commonly tracked using Gantt charts. A Gantt chart is a bar chart that shows the schedule of tasks over time, with each task as a horizontal bar spanning its start and end dates. In practice, these charts were printed on large sheets of paper and taped to the wall of the project room. They might cover entire walls. The problem is that a printed Gantt chart is out of date the moment it is printed. Software development rarely proceeds exactly as planned. Tasks run over. This slide addresses Boehm's cost of change, a concept from Barry Boehm's 1981 book, Software Engineering Economics. Boehm analyzed data from real waterfall projects at IBM during the 1970s. He found that the cost of fixing a defect grows dramatically the later it is discovered. This slide shows the V model. Let me describe what this diagram looks like and what it means. The V model gets its name from its shape. Imagine the letter V. On the left side, going downward, you have the development phases in sequence. Business requirements at the top, then system requirements, then high-level design, then detailed design, and finally coding at the bottom point of the V. On the right side, going upward, you have the corresponding testing phases: unit testing, integration testing, system testing, and acceptance testing. The critical feature of the V model is the horizontal connections. Each level on the left side has a direct corresponding level on the right side. Business requirements at the top left correspond to acceptance testing at the top right. Detailed design at the lower left corresponds to unit testing on the lower right. This means that when you write requirements, you are simultaneously planning how you will verify those requirements. When you create a detailed design, you are also defining what unit test will validate that design. The V model was developed partly in response to Waterfall's weakness of delayed testing. Testing is no longer an afterthought at the end. It is planned from the beginning, with each phase of development paired with a corresponding phase of validation. However, the V model still has the fundamental Waterfall weakness. It is largely sequential. You still do all requirements before all design, before all coding. Rapid prototyping emerged as another response to Waterfall's limitations, particularly the problem of unclear requirements. A prototype is a quick, rough implementation of part of the system, built specifically to answer a question or demonstrate a concept. It is not meant to be production code. Prototyping is used in two main ways. First, to understand requirements for the user interface. Rather than writing a long requirements document and hoping users can visualize what the final system will look like, you build a clickable prototype. Users interact with it, give feedback, and you discover requirements you would have missed otherwise. Second, to determine whether a proposed design is feasible. Before committing to an architecture, you build a small proof of concept to see if it actually works. But prototyping comes with serious risks. The most common problem is that users, or worse, management, look at a working prototype and assume the product is nearly done. They do not understand that the prototype is a throwaway, built quickly, and not intended for production. This can create enormous pressure to ship something that was never designed to be maintainable. A related problem is that a prototype is only a partial specification. It shows some of what the system does, but not all. It can create a false sense of completeness. This slide shows a diagram of phased lifecycle models. Let me explain what this represents. A phased lifecycle breaks the full development effort into a series of phases or iterations, each of which produces a working increment of the system. Imagine the full requirements of a system divided into 3 chunks. Phase 1 delivers the core functionality. Phase 2 adds the next set of features on top of that working base. Phase 3 completes the system. Each phase typically contains its own mini-cycle of requirements, design, implementation, and testing, so the overall structure is several small V models or waterfalls stacked in sequence, each building on the last. The key advantage over a single large waterfall is earlier delivery of value. Users get something working after Phase 1. They can give feedback before Phase 2 begins. Requirements for later phases can be refined based on real experience with earlier phases. This was a significant improvement over pure waterfall. It reduced the risk of discovering at the very end that the entire system missed the mark. It introduced the idea of iterative delivery. Phased life cycles are a conceptual ancestor of the more sophisticated iterative and agile approaches that followed. This slide shows the spiral model developed by Barry Boehm in 1986. The diagram has a distinctive shape, a spiral. Picture a set of concentric arcs, like a coiled spring viewed from above. Each loop of the spiral represents one complete cycle of development, and each cycle takes you further out from the center. The spiral is divided into 4 quadrants. The first quadrant, starting at the top left, is planning. In this quadrant, the team identifies objectives, alternatives, and constraints. What are we trying to achieve? What options do we have? The second quadrant, top right, is risk analysis. The team evaluates the alternatives and identifies risks. What could go wrong? How likely is it? How bad would it be? The team may build prototypes here to reduce uncertainty. The third quadrant, bottom right, is engineering. The team actually develops and tests a version of the product for this cycle. The fourth quadrant, bottom left, is evaluation. Stakeholders review what was built. Their feedback informs the planning of the next cycle. Each loop of the spiral produces something more complete than the last. Early loops might produce requirements, documents, or prototypes. Later loops produce working software. The distinguishing feature of the spiral model is its explicit focus on risk. At every cycle, you assess what the biggest risks are and address them before committing to more work. This prevents the waterfall problem of discovering a fatal flaw only at the end. The Rational Unified Process, often called RUP, is a comprehensive software development framework originally created by Rational Software, which was acquired by IBM in 2003. RUP organizes development into 4 phases. The inception phase is about establishing scope. What is this project? What is the business case for building it? The team works to get stakeholder buy-in and agrees on what the system is and is not going to do. The elaboration phase is where the team identifies and manages the biggest risks. They work out the system architecture. The focus is on the high-risk items, the things that, if wrong, would cause the project to fail. Elaboration produces a stable architectural baseline. The construction phase is where the bulk of development happens. The team iterates and builds operational versions of the system. They also develop documentation and training materials. The goal is a complete working product. The transition phase is about getting the software into users' hands. The team fine-tunes the product based on feedback and resolves configuration, installation, and usability issues. User acceptance testing happens here. RUP is not a single fixed process. It is a framework that organizations customize. You select the activities, roles, and artifacts that are appropriate for your project size and context. Let us look at what each of the 4 RUP phases actually involves in more detail. Inception is about business planning and requirements gathering. The team is asking, does this project make sense? Is it worth doing? What are the broad requirements? Elaboration is more technical. The team identifies use cases, descriptions of how users will interact with the system. They develop a project plan. They design the architecture. They may build prototypes to reduce the highest priority risks. Construction is where development, unit testing, and quality assurance happen. The team is building the actual product iteratively. Transition covers user acceptance testing, where real users validate the system against their needs, as well as training users and administrators. RUP was influential because it brought together many good practices into one organized framework. It recognized that different projects need different amounts of each phase. A small, low-risk project needs very little inception work. A large, safety-critical system needs extensive elaboration. However, critics of RUP argued that it is heavy. The documentation requirements and process overhead can slow teams down, particularly on smaller projects. This criticism contributed to the rise of what came next, agile methods. We now come to agile methods. This slide marks a transition point in the lecture. Everything we have covered so far, waterfall, V-model, phased life cycles, spiral, RUP, belongs broadly to the planned or traditional approach. Agile methods emerged as a deliberate reaction against that approach. In the next several slides, we will explore what Agile means, where it came from, what its core principles are, and what the most widely used Agile methods look like in practice. So what exactly is Agile? Agile refers to a group of software development methodologies that were created as a reaction against the heavily regulated, rigidly managed use of waterfall. Picture a spectrum. On one end, you have what critics call pure waterfall, exhaustive documentation before any code is written, rigid phase gates, formal approvals at every step. On the other end, you have what is sometimes called cowboy coding, no process at all, everyone does whatever they feel like, no planning, no documentation. Agile sits deliberately between these extremes, but closer to the flexible end. The Agile movement developed in the mid-1990s and initially under the label lightweight methods. The most popular ones that survived and grew are Scrum, introduced in 1995, and Extreme Programming, also called XP, introduced in 1996. The word Agile itself as an umbrella term was first used in 2001 when a group of practitioners gathered in Utah to write down the principles they shared. That meeting produced the Agile Manifesto Sextejadur, which we will look at next. The Agile Manifesto is a short document, but it has had an enormous influence on the software industry. Let me read it to you. The preamble says, "We are uncovering better ways of developing software by doing it and helping others do it. Through this work, we have come to value the following: individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, responding to change over following a plan." And then the manifesto adds, that is, while there is value in the items on the right, we value the items on the left more. That last sentence is important. The manifesto is not saying that processes, documentation, contracts, and plans have no value. It is saying that when there is a conflict, the items on the left take priority. This is a value statement, not a set of rules. It tells you how to resolve trade-offs when you face a choice. The manifesto is available at agilemanifesto.org if you want to read it in full. It is short enough to read in 2 minutes. The Agile Manifesto is supported by 12 principles. Let us go through the first 4. Principle 1. The highest priority is to satisfy the customer through early and continuous delivery of valuable software, not documentation, not designs. Working software delivered early and kept coming. Principle 2. Welcome changing requirements, even late in development. Agile processes harness change for the customer's competitive advantage. This is a direct inversion of waterfall thinking. Waterfall tries to freeze requirements. Agile accepts that requirements will change and treats that as a feature, not a bug. Principle 3. Deliver working software frequently, from a couple of weeks to a couple of months, with a preference for the shorter timescale. The goal is short feedback cycles. Deliver something, get feedback, incorporate it. Principle 4. Business people and developers must work together daily throughout the project, not just at the beginning to write requirements and at the end to accept the product. Daily collaboration throughout. These 4 principles together paint a picture of a process that is customer-focused, change-tolerant, fast-cycling, and collaborative. Principles 5 through 8 continue the theme. Principle 5. Build projects around motivated individuals. Give them the environment and support they need, and trust them to get the job done. This is a statement about team culture. Agile teams should be empowered, not micromanaged. Principle 6. The most efficient and effective method of conveying information to and within a development team is face-to-face conversation. Written specifications are an imperfect substitute for talking directly. Agile favors conversation over documentation. Principle 7. Working software is the primary measure of progress, not pages of documentation, not percentage complete on a Gantt chart. The question is, does it run? Does it do what users need? Principle 8. Agile processes promote sustainable development. The sponsors, developers, and users should be able to maintain a constant pace indefinitely. This is a reaction against the crunch culture common in software projects, where teams work brutal hours near deadlines. Sustainable pace means no heroics, no burning people out. The final 4 Agile principles round out the picture. Principle 9. Continuous attention to technical excellence and good design enhances agility. This is an important counterbalance. Agile is not an excuse to write sloppy code. In fact, good code is what keeps you moving fast. Bad code accumulates as technical debt and slows the team down over time. Principle 10. Simplicity. The art of maximizing the amount of work not done is essential. Build what is needed. Do not build what is not needed. This sounds obvious, but it is remarkably easy to build features that nobody asked for and nobody uses. Principle 11. The best architectures, requirements, and designs emerge from self-organizing teams. This is a claim that good solutions arise from teams that have autonomy and ownership rather than from top-down command and control. Principle 12. At regular intervals, the team reflects on how to become more effective, then tunes and adjusts its behavior accordingly. This is the retrospective, a structured moment of self-examination. What went well? What did not? What do we change for the next cycle? Taken together, these 12 principles describe a way of working that is disciplined, but adaptive, fast, but quality conscious, collaborative, but self-directed. Let us now look at the first major agile methodology in detail, extreme programming, or XP. XP was introduced by Kent Beck in 1999. The word extreme refers to taking good programming practices and turning the dial all the way up. XP uses frequent releases in short development cycles. Rather than one big release every year, you release every few weeks. Work is managed by features, described as user stories or use cases. A user story is a short description of a feature from the user's perspective. The team plans which stories to complete in each release and each iteration. Continuous integration means that developers merge their code into the shared codebase frequently, at least daily, and automated tests run to catch integration problems immediately. Pair programming is one of the more controversial XP practices. Two developers sit at one computer. One writes the code. The other reviews it in real time. It is continuous code review. Research suggests it catches more defects and produces better designs, though not all teams find it practical. All code must have unit tests. Before you write a function, you write a test for it. This practice is called test-driven development. XP also advocates avoiding programming of features until they are actually needed. This is called YAGNI, you ain't gonna need it. Do not build features speculatively. Other XP practices include simplicity and clarity in code, frequent communication with customers and between coders, expecting changing requirements, a shared coding standard, collective code ownership where any developer can change any part of the code, and maintaining a sustainable pace. This slide shows a diagram of an XP cycle from an alternate perspective. XP's inner loop typically looks like this. A developer picks a user story. They write a failing test for a small piece of functionality described by that story. They write the minimum code needed to make the test pass. Then they refactor the code to clean it up, keeping the test passing. This cycle, write a failing test, make it pass, refactor, repeats many times per hour. It is called the red-green refactor cycle, named after the colors test runners typically use: red for failing, green for passing. Zooming out, stories are grouped into iterations, typically 1 to 2 weeks long. At the end of each iteration, the team demos what they built to the customer and plans the next iteration. Zooming out further, iterations are grouped into releases, typically every few months. The diagram on this slide is likely showing one of these nested cycles, illustrating how the short inner loops of test and code feed into the medium-sized iteration loops, which feed into the longer release planning cycle. This slide shows a second diagram related to the XP process, likely showing the flow of work through the team or the relationship between different XP practices. In XP, the customer is an active participant, not a passive recipient. They write user stories, they set priorities, they are available to answer questions from developers. The team uses a planning game to decide what to build in the next iteration. The customer chooses the stories with the highest business value. The developers estimate how long each story will take. Together, they decide what fits in the next iteration. On-site customer presence is ideal in XP, having a real user sitting with the team to answer questions immediately. In practice, this is often approximated by a product owner who represents user needs. The diagram is likely representing how these roles and practices connect, how customer input flows into planning, how planning feeds development, and how completed work cycles back to the customer for feedback. The key point is that XP is not just a collection of technical practices. It is also a social model for how customers and developers work together. The second major Agile methodology is Scrum, introduced by Ken Schwaber and Mike Beadle in 2001. Scrum defines 3 roles. The product owner represents the customer and stakeholders. They own the product backlog, the prioritized list of everything the team might build. The development team does the actual work. The Scrum Master facilitates the process, removes obstacles, and protects the team from outside interference. Work is organized into sprints, which are fixed-length iterations, typically 2 to 4 weeks long. At the start of a sprint, the team commits to completing a set of stories from the product backlog. Stories are described and sized in points, an abstract unit of effort relative to other stories. The team does not commit to hours. They commit to a number of points worth of work they believe they can complete in one sprint. The product owner selects which stories the team will work on based on their point capacity and the business priority of each story. At the end of each sprint, the product owner reviews the completed stories. They test them against the acceptance criteria and provide feedback. Stories that meet the definition of done are accepted. Stories that do not are returned to the backlog. Each day during a sprint, the team holds a short daily stand-up meeting, sometimes called the daily scrum. Each team member answers 3 questions. What did I do yesterday? What will I do today? Are there any impediments blocking me? Scrum has an interesting piece of history related to a fable. Early versions of Scrum used an analogy from a story about a pig and a chicken to describe different levels of commitment to a project. In the fable, a pig and a chicken are discussing opening a restaurant together. The chicken proposes they call it ham and eggs. The pig declines, saying, "For you, this is just an investment. For me, it is total commitment." In Scrum, people were classified as either pigs or chickens. The pigs, the committed ones, were the project owner, the Scrum Master, and the development team. They had real skin in the game. The chickens, the involved but not committed, were customers and executive management. They had input, but they were not doing the daily work. There was also a third category, the rooster. The rooster struts around offering unsolicited, uninformed, and unhelpful opinions. You will recognize this character in most organizations. In 2011, this fable was formally removed from the official Scrum guide, lect-mwila Scrum. It was felt that the pig and chicken terminology was disrespectful and created an unhealthy us versus them dynamic between the development team and stakeholders. The underlying insight that different people have different levels of commitment is still valid. The fable just became an awkward way to express it. This slide contains a diagram that is likely showing a Scrum board, a sprint burn-down chart, or the Scrum cycle. A Scrum board is a visual tool for tracking work during a sprint. It typically has 3 columns: to do, in progress, and done. Story cards move from left to right as work progresses. At a glance, the team can see how the sprint is going. A burn-down chart is a line graph showing how much work remains in a sprint over time. The horizontal axis is the days of the sprint. The vertical axis is the remaining story points. An ideal team would see a straight diagonal line from the total points at day 1 down to 0 at the last day. If the real line is above the ideal line, the team is behind. If it is below the ideal line, they are ahead. The burn-down chart is a simple, honest measure of progress. The Scrum cycle itself shows the relationship between the product backlog, the sprint planning meeting, the sprint, the daily Scrum, the sprint review with the product owner, and the retrospective. Whichever of these this diagram shows, the central message is that Scrum is a highly visible process. Progress is visible to everyone, problems surface quickly, and the team continuously adjusts. The next 3 slides represent personal experience and opinion from the lecturer who created this material. This is valuable because it bridges theory and practice. Feature-driven development, the idea of planning and delivering work one feature at a time, is widely accepted. Almost nobody believes in pure waterfall anymore. But the way features are specified matters. Writing full requirements, specifications, and design documents for an entire release before starting development is essentially waterfall, even if you call it something else. Writing requirements and design documents per feature, only when necessary, is different. This is actually advocated in agile approaches. The point is, do the planning work that is necessary and no more. Continuous integration, keeping the code in a working state at all times, is strongly recommended. If you let the code base drift into a broken state, the cost of recovery grows with time. Automated architectural regression testing is also recommended. This means tests that verify not just that individual functions work, but that the system's overall structure has not been inadvertently degraded. Full unit tests for all code. In practice, this is often unrealistic. Coverage matters, but 100% coverage is rarely worth the investment for every type of code. Pair programming, sometimes useful, not always practical, depends on the team and the task. Frequent communication, including involving stakeholders? Yes, strongly, but you cannot force stakeholders to attend if they will not show up. Continuing with personal experience from practice. Committing only to the next sprint without any longer-term view. In practice, this is not realistic. Stakeholders and management need to know roughly when things will be ready. A team that refuses to give any forward visibility beyond 2 weeks creates frustration. Using story points instead of time estimates. The experience here is skeptical. Everyone outside the development team, managers, customers, executives, will not trust an abstract unit they cannot relate to time. Coding standards and collective code ownership? Yes, these are practices that pay off consistently. Eliminating the final test phase entirely? Not practical. What you can do is reduce the need for a large final test phase by doing code and test iterations throughout the coding phase. But some final verification is usually necessary. Using working software as the primary measure of progress, mostly yes. But for large releases, the recommendation is to supplement this with featured demos during development, independent functional testing during coding, and a reflection on the release plan when each feature meets the definition of done. Planning to a date called feature complete, or DCUT, means relentlessly tracking when all features will be complete. This is a practical way to maintain schedule visibility. The final slide of personal experience addresses some of the more idealistic Agile principles. Welcoming changing requirements at any time. You cannot avoid changes. Requirements will change. But the recommendation is to welcome changes within a planning framework. You cannot accept every change without considering the impact on end dates and on the team's workload. Unconstrained change is not agility, it is chaos. Sustainable development? Yes, in principle. But it is unrealistic without careful planning. Sustainable pace does not happen automatically. It requires realistic estimates, scope management, and the willingness to say no to new scope when the team is already fully committed. The best architectures emerging from self-organizing teams? The experience here is unconvinced. Good architecture usually requires at least some deliberate design work by people who understand the system as a whole. Pure emergence can lead to inconsistent, hard-to-maintain systems. And finally, a warning. It is easy to proudly declare that your team is agile while actually doing cowboy development. No planning, no documentation, no process at all. Genuine agile is disciplined. It has rituals, artifacts, and accountability. If your team calls itself agile but does none of those things, it is probably just disorganized. The test is simple. Are you actually delivering working software regularly? Are you actually reflecting and improving? If not, the label is cosmetic. So which process is the best? The honest answer is it depends entirely on the context of the project. Every process has advantages and disadvantages, and those trade-offs look different in different situations. Consider a question. Does continuous deployment make sense for the next version of Microsoft Office? Office has hundreds of millions of users across every industry. A breaking change could be catastrophic. Extensive testing, careful release management, and controlled rollouts are essential. Continuous deployment in the Agile sense would be very risky. Now consider an X-ray machine. This is safety-critical software. A bug could cause a patient to receive a fatal radiation dose. Would you use an Agile process with minimal documentation and rapid feature delivery? Probably not. You would want exhaustive formal specification, rigorous verification, and formal certification. Now consider something even more extreme. The Space Shuttle avionics. NASA used a language called HAL/S developed specifically for the shuttle. The primary and backup avionics systems were developed completely independently by different teams so that a shared bug in one could not propagate to the other. This level of rigor was appropriate given the consequences of failure. And then consider the Curiosity rover on Mars. The software was installed on the rover during its flight to Mars, and then upgraded while it was on Mars using a remote update process. That required a completely different set of process concerns. The lesson is, match the process to the project. Consider the consequences of failure. Consider the rate of change of requirements. Consider the size and distribution of the team. No single process is universally best. We close with a summary diagram. Let me describe what it shows. The diagram places Agile Horizon at the center, representing a spectrum between chaos and heavy process. Around it are arranged the practices and concerns that define mature software development, regardless of which specific SDLC model you follow. Source code control is non-negotiable. Every professional software project must have a version control system. Without it, you cannot collaborate, you cannot roll back changes, and you cannot understand the history of the codebase. Infrastructure control means managing your servers, build pipelines, and deployment environments in a consistent, repeatable way. Reproducible builds mean that anyone on the team can produce the exact same binary from the same source code. If your builds are not reproducible, debugging production issues becomes very difficult. Automated regression testing means that every change to the code is automatically verified against a suite of tests. This is what keeps the code base healthy as it grows. Feature specifications, written when needed, keep the team aligned on what is being built and why. Architectural control means actively maintaining the quality and consistency of the system's design over time. Effort tracking and planning give the team and stakeholders visibility into progress and workload. Business planning connects the technical work to the organization's goals. The message of this summary is simple: do these things and you are doing well. Whatever specific SDLC label you put on your process, these fundamentals are what distinguish professional software development from cowboy coding. That concludes our lecture on software development lifecycle models and agile methods. Thank you.